before we get into the topics, how many of you hate or fear chemistry?
No, I hate it.
Okay. Tell me what you hate or fear about it.
Math. Math.
Math. We're not doing any of it.
Very good.
Anything else?
Everything's like similar.
Complicated, yeah. So it's really tiny, you can't see it happening. I'm going to do a lot of analogies, try to make it like the chemicals are people and they have motivations that are why they do what they do. And even though that's not really how it works, at least we don't think so because you can't ask an atom what it's thinking, it's a useful way to describe it. Okay. Anything else you're worried about? Right. Now, why do we care about chemistry in anatomy and physiology? First off, a couple of definitions. Chemistry is the study of substances, what they're made of, and how they can change. Biochemistry specifically studies substances in living things. Physiology is largely based on chemistry. How the chemicals interact affects how things work. And then even in anatomy, the structures are made of chemicals, even if those chemicals are combined into cells. Matter is the scientific word for stuff. Matter has two properties. It has weight, which means gravity can pull on it, and it takes up space. The major states of matter that you'll encounter are solid, liquid, and gas. So solid like your desk. We mostly seem to be solid, although there's a lot of liquid in us. Liquid like your coffee, and of course what's the major liquid in the body? Water. And then gas like the air we're breathing. Now in physics, instead of weight, they're going to say mass. Technically, mass is the measure of how much stuff there is, and weight is the pull of gravity on that mass. So if you were to start working with astronauts, you might have to be more specific about the difference, but as long as we're on Earth, mass and weight are basically the same. Elements are fundamental types of matter, like things found on the periodic table. Examples would be hydrogen, gold, arsenic, oxygen, calcium, anything that has a box on the periodic table. Compounds are substances that are made of more than one element. Like water, H2O, has hydrogen and oxygen. That's two elements, so water is a compound. Whereas something like helium gas or carbon, by itself, those are elements. In the body, we can divide what elements we've got into two categories. Bulk elements we need in large amounts, and they make up a large portion of our weight. There are 6 top bulk elements that combined make up 95% of our body weight. And these also have easy abbreviations because it's just the first letter of their name. Carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. And out of those, the first 4 are the really big ones. Trace elements are things we need in smaller amounts like calcium, sodium, and potassium. Out of those, the only one that likely makes up a measurable portion of our weight is calcium, because there's a lot of it in our bones. A lot of trace elements are things you'll see on a vitamin and mineral supplement. Questions on elements? Atoms are the smallest possible unit of an element. I said last week when we talked about levels of organization, atom means no cut. It's the same tom as in anatomy, cut up. If you cut an atom any smaller, you no longer have the properties of the element. Atoms are made up of subatomic particles, and they can attach to each other through chemical bonds. Let's start with the subatomic particles. Now, here's also a study tip, making tables. Anytime you can organize information in a table, that may be easier for you to look at and understand than if you write it all out. So we're going to make one for the properties of subatomic particles. The main thing to know about each subatomic particle is its charge, its mass or weight, and where it's found in the atom. The three types are protons, neutrons, and electrons. Each of them has a different charge. Proton is positive, electron is negative. These are arbitrary terms. It doesn't mean a proton's good and an electron is bad. It just means that they're opposites. I read somewhere that it was Ben Franklin that came up with the idea of calling them positive and negative. A neutron is neutral. So it doesn't have a charge the way these two do. Atoms are so small that we use a special unit to measure their weight. It's called either an atomic mass unit, or AMU, or a Dalton. And it's equal to the weight of one proton. So a proton's going to weigh 1. A neutron is about the same weight as a proton. Tiny bit heavier, but not enough to be worth worrying about. Electrons are so tiny that for our purposes, calculating the weight of an atom, we're going to count them as 0. They actually have measured them, and almost 1,800 of them are needed to match the weight of a proton. Location ties in with this diagram. The major parts of an atom are the nucleus, a cluster at the center, protons and neutrons are both in the nucleus, and then the electrons are outside the nucleus in an area that's sometimes called an electron cloud. To help us understand the properties of the electrons in that cloud, we organize it into areas called shells. For simplicity, we draw shells as orbits, only instead of just having one electron in each, like planets in an orbit, they can have multiples. And that's not really what the shells look like, but it's a convenient way of visualizing them to understand the structure of a particular atom. So any questions on these subatomic particles? The periodic table is a way of organizing all the known elements. When you go across, you go up, and then you start over and go across again. So number 1 is up in the top and on the left. The location tells you something about the positions of electrons as well, which we'll get to coming up. And then each one has a little symbol for it. So, what's on the periodic table for each element? Some tables have a lot of additional information, like melting point, freezing point, and so on. We're just going to worry about 3 of them. On the slide, I have hydrogen. Here I'm going to do carbon. The letter is the symbol. That's the official abbreviation for that element anytime it's used. Most of the ones that you'll need to remember, it's just the first letter of the name. There are some that are 2 letters. When that happens, you capitalize the first one, but the second one is in lowercase, like calcium is Ca. And it'll always be capital C, lowercase a. And then some of them are kind of weird, not what you'd expect, because they come from the Latin name for the elements. The 2 that you'll need to know later on that work that way are sodium and potassium. The Latin word for sodium is natrium, and for potassium is kalium. We do that to be universal, so no matter what language you're using, you have a consistent symbol. And then there are 2 numbers to know about. On the top is the atomic number. That's equal to how many protons are in the element. And this actually is what determines the element. The number of protons determines the element's properties. Anyone heard of the old alchemists that were trying to turn lead into gold? Here's lead. Its atomic number 82, so it has 82 protons. Gold is over here, atomic number 79. So if you could remove 3 protons from the nucleus, you would turn lead into gold. Physicists can't actually do that today. There's 2 reasons that it's not worth doing most of the time. 1, it's more expensive a process than the gold you get. 2, you get radioactive gold. But you change the protons, you change the properties. So hydrogen, as you can see there, has 1 proton. Carbon has 6. Then at the bottom is the atomic weight or atomic mass, or sometimes called a mass number. Now, if you were looking at just one atom, that would be equal to the number of protons plus the number of neutrons, because each of those weighs 1. And usually, they're close to each other. Something with 6 protons will have around 6 neutrons. It could have 7 or 8. Something with 12 protons would have close to 12 neutrons. But because there's some variation, this mass number is the average of all of the atoms, I think, on Earth. It might be the average of what we estimate in the universe. So most carbon has 6 neutrons, so it would have 6 protons plus 6 neutrons gives it a weight of 12. But if it had 7 neutrons, then its weight would be 13, because it's still 6 protons. Okay. So if it had 8 neutrons, but still 6 protons, then its weight is 8 and 6. Okay, so we're doing a little math. 14. Okay. So if you have the same number of protons, but a different number of neutrons, you're the same element. We call the different numbers of neutrons isotopes. So carbon with 6, 7, or 8 neutrons is still carbon as long as it has 6 protons. If we were just talking about carbon in general, we'd just say carbon. But if we wanted to specify an isotope, we would add the number of its mass. So carbon 12, carbon 13, carbon 14. Has anyone heard of carbon 14? It is slightly radioactive, not enough to cause any damage, but enough to measure. They use it for figuring out how long ago something died based on how quickly the carbon 14 decays. It decays at a specific rate. So however much of it is left tells you how old it was. Right, questions on atomic properties and isotopes? One of the ways to put atoms together gives us molecules. A molecule means atoms are sharing electrons, which is something called a covalent bond that we'll talk about coming up. Molecules are indicated with a molecular formula, which includes the symbols for all the elements in it and a subscript number for how many of that atom is in the molecule. So you may have seen oxygen written as O2. What that means is it has 2 atoms of oxygen that are joined together. H2O means it has 2 hydrogens and 1 oxygen to make a molecule of water. This one here, it would have 6 carbons, 12 hydrogens, and 6 oxygens. Anyone know what this is? Sugar. Yep. So anything you see that's written like that, it's indicating a molecule. Now, we talked about molecules and compounds as ways that atoms could combine.